Okay, so off we go. Last time I wasn't here, so very glad to be back. Thanks for y'all's patience and understanding given my illness, but all's good. I'm all recovered and everything. Anyway, where y'all were last time was talking about injectivity and surjectivity and all this kind of business. Our most immediate purpose for which is to talk about what do we mean by invertibility. Right? What does it mean for a function to be invertible? And why does that matter? Well, because sometimes you want to talk about the inverse of a function, and you can't talk about the inverse of a function if you don't even know if it's invertible. Okay, so with that definition having been made, we can address a couple of specific cases. And this is just algebra, so I'm going to be pretty quick with this stuff. But a lot of people are told, as I was, in, elementary school or whenever they start talking about square roots, that square root means you're just undoing the square function. And that's just importantly not true, right? So here's the function that squares things. You can put in any real number, right? And if you're open-minded, you can accept any real number as an output, right? Not knowing necessarily what the properties of this function are. So that's what you might call the squaring function, and it's pretty clearly not invertible, right? There are plenty of values in the target for which there are 0 preimages. And there are plenty of values in the target for which there are 2 preimages. This is not an invertible function, right? So to get something that is invertible, so that we can talk about the square roots, you have to restrict the domain and the target. And this is a good way to do it. This is the standard way to do it right here. You notice we only allow non-zero inputs, and we only allow, of course, this is all we were going to get anyway, but we specifically only allow non-negative outputs. And in so doing, this function actually is invertible, because for every non-negative real number, there is exactly 1 non-negative preimage. Right? And that is what we call the square root. So the square root function is literally, this right here is the inverse of the invertible square function. Right there. So similar story with sine x. If you just look at the regular old, real in, real out, f of theta is sine theta. Stick with this dummy variable. That function's not invertible. It's not. Right, and you may have seen various different treatments of this in a high school trig class. I saw some, what in retrospect I now realize was complete nonsense. Garbage ideas. They're trying to salvage, different notions of inverting the sine function, when in fact it's so much easier and more appropriate just to say, yeah, it's not invertible. Let's make it invertible and then talk about its inverse. Right? So all you have to do is, like I have indicated here, just restrict your domain. This is the standard restriction of the domain to these values of theta from negative pi over 2 to pi over 2, like so on the unit circle. And then furthermore, restrict your target to just negative 1 to 1, like so on the unit circle. And then this resulting, this what you might call portion of the graph of the sine function, that is the graph of this, what I like to call the invertible sine function, and that function is invertible, no problem. Arc sine is just the inverse of that invertible function. Happy ending. Okay. All right. So for whatever it's worth, it is a lot of students like to think about functions in terms of the graph, and so looking at this picture right here is perhaps the more common approach. But I want to encourage you all to think about it in these terms, right? Because it's really more sort of fundamental. If you think about how do we actually define the sine function, it's off of the unit circle. The unit circle is really the best way to define what we mean by the sine of an angle. And The sine function then is just that. You give me an angle on the unit circle, look at the y-coordinate, that tells me the value of sine of that angle. And then arc sine, in this same picture, arc sine is just go the other way. Nice and simple. Couldn't be easier. Okay. All right. Okay, a couple other things that have to get said. A little bit of terminology. If you have a function that may have multiple inputs, may have multiple outputs, how do we describe such a function in words? And so in particular, if you look at the number of outputs, that tells you, what valued that function is. So if there's only one output, the outputs are real numbers or scalars, and so this is called a real valued or scalar valued function. If, however, m is greater than 1, if there are several output values, right? You're looking at this here, right? Several output values. You might say the output is a vector. Then we call that a vector valued function. Okay, so just a little bit of terminology. Likewise, the number of inputs, we refer to the inputs as variables. Keep in mind, sometimes we talk about input variables, output variables, but in this context here, variable is a reference to the input variables. And again, could be single variable if there's one input, could be multivariable if there's more than one input. Okay. Let's see here. Take a quick look at this idea of component functions. Here, altogether, this function, let me do it like this. This function here, but let's look at it from this point of view, has multiple output components. If you view just y1 as being a function of these several inputs, that's what we call the y1 component function. So all of the variables depend on all of the inputs, right? But if you look at just one of the outputs alone, still a function of all of the inputs. That is itself now a new function. We call this a component function. Okay. All right. There's a temptation for people to look at, this seemingly complicated construction, a vector-valued multivariable function. It's a mouthful, right? And it sounds like we're talking about something sophisticated and far out, and therefore correspondingly, rare, perhaps. And it's really not. This is a very, very common story to find. Is that you have a function that is vector-valued and multivariable. And so just to drive this point home, I like to talk about the weather. Again, about as unabstract as you can get, right? This is just basic water cooler conversation, trivial, trite nothingness, nothing sophisticated at all, and yet it is a multivariable function because look at all the input variables, right? If you're going to talk about the weather, it depends on where you're talking about and when you're talking about. And by the way, let's not forget to pay attention to altitude because the weather 30,000 feet up is very, very, very different from the weather here at ground level. And this is a vector-valued multivariable function because, there are various different aspects of weather that, you really should keep in mind if you want to understand the weather. And so multiple outputs means vector-valued. Okay, so anyway, easy, real-world, highly relatable example. Nothing abstruse, nothing ivory tower, right? And yet it's a vector-valued multivariable function. Okay. Yeah.
So here, by multivariable, you mean multiple inputs?
Yeah, that's right. The term variable, when you're talking about multivariable, this is a reference to input variables. Yeah, just convention. Right. Okay. Okay, visualizing functions. This is harder than it's going to seem at first glance. This is surprisingly subtle. A lot of students underestimate the challenge that's involved with what we're about to talk about, how to visualize multivariable functions. The reason I think that students underestimate this material is that if you kind of look at the algebra that we're about to write down, it's pretty trivial. It's kind of algebra 1. We're not going to so much as use even as much as the quadratic equation. I mean, this is pretty straightforward, just kind of moving terms around. Algebraically, in terms of the algebraic manipulations, there's not much to it. What there is a lot of is subtle distinctions and important consequences to these subtle distinctions, and a past history that many of y'all have of kind of getting away with being wrong with some of these distinctions. It's not your fault. It's your high school teacher's fault. Let's blame them. They're not here. They can't defend themselves. Right? But certainly when I was in high school, I was allowed to get away with murder on a lot of things that in retrospect, I just, oh God, I can't believe I would say, I know I said, oh God, that's horrible. So what you should be focusing on as we go through this stuff is the precise definitions, not a sort of a, I kind of see how that works, or I see the pattern, I can execute that, right? Think carefully about the precise definitions. Be careful with your terminology. It is surprisingly difficult, if you are accustomed to saying things a certain way, to kind of train yourself out of that, and you can inadvertently talk yourself into some pretty nasty mistakes if you are sloppy with language. So I'm going to do my best to not be annoying when y'all say something, in this general area. If you say it wrong, I'm going to correct you. I don't mean to be annoying, right? But it is important that we get that fixed, because otherwise, like I say, you'll get some pretty dramatically wrong answers if you're sloppy about these things. So think about being careful. Think about being precise. Okay. All right, so we're going to start off with the idea of a graph, and I know y'all have seen graphs before, yawn, right? Seemingly nothing to it. Let's real quick go to the standard single variable example. Here's a Calc 1 style function, and if I say single variable function, yeah, boring. If I write down y equals f of x, boring. If I draw this picture, boring. Okay, but let's think exactly what happened here. How did we get that picture from this abstract algebraic construction that is a function that takes one input and gives one output? And by the way, a little bit weird if you think about it, the domain here is one-dimensional. There's not a function of two variables. Target is one-dimensional. Everything involved in the definition of this function is one-dimensional. How can we have a two-dimensional picture? I don't know if you ever thought about that before. This kind of weirded me out the first time I made that realization. So here's the process. The process is we're going to take inputs to the function, like this x here. All the inputs get listed first. Now, of course, there's only one in this case. And then we're going to look at the corresponding output value. That and all other output values, however many there may happen to be, come next. And then we're going to say, okay, we're going to look at this odd little point right here. This is a weird point, this thing x comma y, because x is in the domain, y is not. So that's weird, right? We're kind of mixing stuff together that doesn't naturally belong together. The target is a completely different world from the domain, right? So we're going to smash them together and make then the coordinates of a new point. Odd though it is, right, on our as a matter of choice on our part, right? We're going to make this point x comma y we're going to plot that in this weird space that we are creating for our selfish purposes, where we put the domain over like that and we put the target kind of like this. We, again, smashing together two separate spaces that don't belong together, really. And that gives us a point on the graph, and then if you do this same process for all of the inputs and collect all these resulting weird points together, then you get this curve, this familiar curve called the graph. So notice that's what we have here in this definition. The graph is a collection of points generated like so, where you take the inputs and the outputs and you put them together as if that was reasonable, right? And the collection of all of those sort of smashed together points is your graph. Okay, does that make sense to everybody? Again, the point here is not that I don't think you've seen this before or that I think you don't know how to do this. The point here is to be explicit about exactly what is it that we're doing when we form that. Okay. Now here's another way to think about it, and a very common and a very convenient way to think about it, and that is to notice that when you have a function, right, f is typically written in terms of a dummy variable, so I can talk about f of x. X is the input, f of x is the output, and now I'm going to make a choice. This is an arbitrary choice. You do not have to do this. We've done it so many times it kind of feels like we have to, but you don't. This is not a requirement. This is a choice. We can choose to take what comes out of this function and call it by another variable name. That's a choice. Right? So we write down the equation y equals f of x. And that equation, now you'll notice, again, there's only one input, there's only one output, and yet we have an equation involving two variables. Right? That is the equation of the graph of that function. Yeah.
Wait, so how are you able to keep it in R1 again?
How to what now?
How are you able to keep it in R1?
What do you mean keep it in R1?
Like you were mentioning how like this technically in R2, but you're
well, okay, yeah. So the target is R1,
yeah,
right? So this is a one variable in, one variable out, right? So as a function, it's kind of one-dimensional in every sense. One-dimensional domain, one-dimensional target. We are choosing to visualize this function by way of this picture that lives in two dimensions. But that's our creation, right? That is not intrinsic to the function. We're making that up.
Okay.
Yeah, we're choosing to make this construction because it helps us understand things geometrically.
But in reality,
it's manufactured.
It's made.
Yeah, it did not come along with the function. Right? This is not intrinsic to what the function is. Yeah. Okay. Yeah, so you can think of a graph as being made up of points where inputs and outputs are all in the same coordinates, or you can think of it as this is what you get when you take a function and set the outputs equal to a new variable. Take a pick. Okay. All right, so let's take that process. Let's do the same thing now with a function of two input variables. So two input variables, x and y. Right, we're going to put the x and y first, as is our process. Here's an input point, x and y. I'm visualizing the domain being sort of down this xy plane down here. Let's see here. Now we have a target that is one-dimensional. We have one output variable, so there goes the output variable. I'm going to put that there. That'll have some value. I'm going to represent that on the picture there. Again, being the output value, that kind of goes there. And now let's look at these points. This was a function that had a two-dimensional domain, right? Two-dimensional domain, one-dimensional target, and yet our picture is now three-dimensional. Right? 2 in, 1 out, altogether makes 3. So, yeah, it's like we're taking the close enough. The one-dimensional target and kind of pasting it onto the two-dimensional domain. And for a given input point, we get a corresponding point on the graph. And keeping in mind now that we do this for every point in the domain is an entire plane, an entire two-dimensional plane of points. You can see the way we have this construction made that for every point in the domain, the corresponding point on the graph just kind of sits right up above it. It's like we're taking every point down here and kind of lifting it up, but of course, different points get lifted by different amounts depending on the value of the function. And the point I'm getting at, though, is that the graph you would expect to be a surface because it comes from kind of lifting this two-dimensional plane. So there you go. That's what a graph looks like for a function of two input variables. There's our first multivariable graph. Yeah?
Will you always make the output variable perpendicular to the other ones?
Yeah, I mean, anytime you draw an axis system, no, overstate it. It is typically considered very convenient for a lot of excellent reasons to want to keep your axes all independent, or orthogonal. Yeah, totally. I'm going to say might as well, and I think we're pretty exclusively going to do that. Yeah. Yep.
Is it possible that a linear transformation can give something like surjective?
Something like what?
Surjective.
Oh, sure. Absolutely. Yeah, that's kind of independent of what we're doing. But yeah, sure, there are plenty of linear transformations that are surjective.
Isn't the graph just going to wrap around like this one x value having?
Okay. Well, now, so I think you meant something different than what you said then. So you said surjective. Surjective means that all of the points in the target are actual outputs of the function, right? So you got to make sure to remember this is the target. The target in this example is just R1, right? So what we're looking at now, we're looking at a picture of R3. This is not the target. This is this weird, I've got this domain, I've got this target, and then I kind of combine them together to make this weird Frankenspace here, right? This is not the target. You see what I'm saying? Yeah. So I'm not sure if does that clarify, or maybe I didn't understand your question.
Just wondering, what is one? Say this is from x to y, and one x value can correspond to two different y values, and the graph is going to look something like a parabola, but
No. So the word function. So a critical aspect of a function is that whatever you put in, there is a unique output. Right. So now that output can have multiple coordinates, like the output could be a vector, right? But you can't have multiple outputs for the same given inputs. So I think if I understand correctly what you're describing, that's not even a function at all.
Oh yeah, I think I understand.
Okay. Yeah. Okay. So picture, right? It's nice to be able to have a picture that goes along with this multivariable function. Sort of our. By the way, let's recognize this is about the simplest multivariable function you can possibly write down. Right? 2 is the smallest number greater than 1 that could make it therefore multivariable, and 1 is the smallest number of outputs you can possibly have. So, I mean, this three-dimensional picture is the simplest possible multivariable graph. And let's entertain now the next natural question, which is, what if we had 3 inputs? And I'm sad to say, this is bad news. With 3 inputs, only 1 output, one step above, you might say, the simplest possible multivariable case. And check it out, we have 4 variables. That means our picture would live inside of R4. This is not something we can possibly draw or visualize. It's just a losing proposition. So, graphs have very limited utility in a multivariable context. Right? There's kind of, I don't want to say that, it's a slight overstatement to say that this is the only possible application, but it's anything higher is we're running out of dimensions. Everybody see the nasty problem? All right. So now I've made this observation. Well, let's see. Did I? I said something similar, but let's say it again. It's very important not to be sloppy about this, right? We don't want to think of the function as being synonymous with the graph of the function. They are really importantly different. A function is an abstract algebraic object, right? A graph is a picture, and just one of many, and arguably not a particularly good one. Certainly in this situation where we dare, entertain so much as a third input variable, right? So the graph is not to be conflated with the function itself. We're going to need to talk about functions that totally exist and that we can totally deal with, but whose graphs we cannot deal with. Right? So you got to keep these objects separate in your mind. And this process of how we form a graph from a function, make sure to understand that this is an arbitrary choice of a process that involves specific steps. Right? It is not just what you do, or that's how functions work, or anything remotely like that. Okay, so let me show you another kind of a picture. This is, I think, a really, really good one. This is one of my favorites, even, and I have not seen an official name given to it anywhere that I recall. So I'm just calling it the literal picture. I think I made that up. I don't know. I may have. It's possible that this is a distant memory that I don't even recall where it came from, that I saw who knows how long ago. But anyway, I'm going to call it the literal picture, which I think is a great choice because I'm literally going to take the domain and draw a picture of it. And I am literally going to take the target and I'm going to draw a picture of it, right? I mean, this is what R3 looks like, best I can do on a sheet of paper anyway. This is what R1 looks like. And what does a function do? A function is the process of taking stuff out of the domain and kind of plopping down its image anyway, into the target, which you see I'm kind of doing with the sort of this arrow that I've got here representing f. And so, for example, that point there has an image that is, let's say, that point there. And that's a picture of sorts. Arguably not a very good one, but it is kind of a picture. Yes?
The kind of notation you use kind of looks similar to like the matrix notation. Does it have to do with anything, or just like a coincidence?
Matrix notation.
As in you describe a matrix as going from, for example, R3 to R1.
Oh, yeah. Well, what this is a general representation of a function. So what you're thinking of as being a matrix was actually how we write the linear transformation that's represented by a given matrix. Right? Again, it's two things that are easily conflatable, but actually kind of different, right? So yes, linear transformation is a function, and functions you describe by, you write the name of the thing, and then colon, and then domain, arrow, target. Absolutely. Yeah. Yep. Okay, so let me defend this seemingly disappointing picture. Right? After all, here's what's disappointing about it. Where's the shape? Shouldn't there be like a surface or like at least a curve or something? Shouldn't I be able to see some geometry, and the shape would tell me something about the function, like we're accustomed to here, right? You look at the single variable, sort of our Calc 1 functions. I can see from this curve slopes and concavity and stuff like that, and that tells me cool information about the function, namely about the derivative and about the second derivative and stuff like that. Right? So the shape is supposed to tell me useful information about the function. Where's the shape? I don't see it. So that stinks and I don't like it, but the comparison that I just made there is completely unfair. That's what we call an apples and oranges comparison. Right? I'm judging this picture on the basis of how it works with, let's face it, a pretty difficult example of a function, 3 inputs, 1 output, but I was comparing that against the much easier challenge for graphs where there's only one input. So if we were to make a apples and apples comparison, I would need to compare this performance of this picture, R3 to R1, with this performance, which was a catastrophic failure. Nothing. I have no picture. I got 0. Useless, right? So when your alternative is to have absolutely nothing, a disappointment is a win, right? Everybody on board? Okay. So now, disappointing though it is, I will point out, this is actually not that bad, and this is exactly the kind of picture that we're going to need for some important questions that we're going to ask, and here's one of them. And we will get to this very soon, I think Wednesday, if I remember correctly. It depends on how fast I go through some of this other stuff. But anyway, very soon, we're going to entertain the following question. Let's suppose I look at this point A, and at that point A, the function has some value, f of A, and the question says, okay, suppose that this input point that goes into the function, suppose that point were to take off and start moving. And when stuff moves, of course, it's got a velocity, like so. Well, if you change the input, obviously that's going to change the output. Specifically, if the input is moving with some velocity, then the output, likewise, you would expect to be moving with some velocity. And reasonable question, given an input velocity, what is the corresponding output velocity? Now, the answer to that question, that's a couple days from now. That's good. We'll talk about how to figure that out and write that down, and that's not my point here. My point is, this is an excellent picture of the question that we're asking. Right? So, pretty useful, actually. Does everybody see what I'm getting at there? Yeah. Okay. All right. So don't underestimate the value of this kind of picture. And again, it's really very natural. Again, there's the domain, there's the target. You're going to see a lot of this kind of picture, and it's a very good picture to be comfortable with. And it's not a graph. Right. Okay. All right. Level sets. So again, there's a bunch of scary-looking symbolic notation there, and I'll make some references to that. But let's look at an example to get the ball rolling. By the way, notice as I get the ball rolling on this, notice I start off with, in fact, this literal picture. The domain, R2, boom, there's a picture of my domain. The target, R1, bam, there it is. There's our target, R1, and you can see the function is represented in this figure as taking points from the domain into the target. So that's kind of cool. All right, so here's how we form level sets. The big idea of a level set is you pick an output value from the target. You put that output value on the right, and then you ask, okay, well, what are the corresponding input values? What are the x's in the domain that when you put them into F, that selected output value actually comes out, right? Or said differently, these x's, they're the pre-image of that output value. And the output value in this case, now how are we going to get that? Keep in mind what this equation says is the output value from the function equals the chosen point in the target. So I'm going to write that down right here. Here's the output values from the function that need to be equal to my selected point in the target. Right? F of x equals whatever I've selected on the right. So x squared plus y squared equals 1, and in this case, that's actually pretty easy to understand. That is just this circle. It's the unit circle in the xy plane. So this green circle is the pre-image of the value 1 for this function, f equals x squared plus y squared, and therefore this is a level set. It is the level set for this output value 1. Okay. All right. Likewise, here's another output value. Let's look at 2. Right, and let's ask the question, what are the corresponding inputs? Right, what is it, if I set the outputs equal to 2, what are the values of the function? What are the inputs to the function that give an output value of 2? And it's a pretty easy pitch, I think, that is just a slightly larger circle. And again, you can just look right at this equation. X squared plus y squared equals 2. Slightly bigger circle. So we're starting to form a picture here. Each one of these circles is a level set. Typically, if we want to understand a function, we pick several output values. We draw then several resulting level sets. And all together, they kind of give us a picture to look at to kind of get some sense for what the function's really doing. So let me show you some examples. You've probably seen something kind of like this before if you've ever gone hiking and carried a topographical map, or if you've ever pulled up Google Maps and hit I think it's called the terrain option on Google Maps, and if you zoom in to just the right level, if you zoom in too much, it doesn't work. If you zoom out too much, it doesn't work. But at just the right zoom level, they will actually have what they call contour lines, and contour lines are level sets. They are level sets of the altitude function, where you pick a given output, namely a given altitude, and then you ask, okay, on my picture, where are all the points that have this altitude? And it might be, so for example, something kind of like that. Maybe that is the collection of points that have that altitude. And then at a slightly higher altitude, maybe it's something that looks kind of like that, let's say, and then you can keep going. You can pick a bunch of different altitudes and look at the corresponding level sets, the corresponding pre-images, casually called contour lines, right? And all together you get this kind of picture, sort of like this. Yeah.
One output can have multiple pre-images.
Oh yeah, absolutely.
So what
So
would that be? Like how to translate to here? Like can you have multiple level sets for one output?
it's all part of the same level set. So for example, you look at this point right here, that point has 2 points in its pre-image. Yeah, absolutely. And in that case, there's only 2 because there's just kind of a finite number of points there. What we're looking at here, there's sort of a dimensional thing going on. Notice that there are 2 dimensions of inputs, but only 1 dimension of output. And so in some sense, there's a lot more inputs than there are outputs, and that's why you can have infinitely many points.
So that's like within one level set. Like
Yeah,
one
each-
level set would encompass like
That's
all
right.
of the
Yeah,
different pre-images.
Yeah, I hear what you're saying. Yeah.
Yeah.
So the word pre-image gets used to mean 2 different things. So a pre-image is a point that is in the pre-image. The pre-image can refer to the set, the entire set of all pre-images. Yeah, the language is a little unfortunate there. Yeah.
Thank you.
Yeah. Okay. Now that's just a something I sketched up, but I'm going to show you a real example of a contour map. So this is a contour map of, I guess they call it a topographical map of a mountain in Colorado. This is a mountain that I climbed when I was about y'all's age or so. So I'm familiar with this area, and I can attest to what it feels like when you're hiking along. And I'm going to talk about how that is represented on the map. So in particular, as you're going along this trail here like that, as you're hiking along in the valley down here. By the way, on this particular topographical map, each pair of contiguous contour lines represent an altitude difference of 40 feet. That's just how they did it. I don't know where they picked that from. You would have thought 50, but whatever. Anyway, 40 feet. Okay, so notice, as you're hiking along this trail, you've got a pretty substantial amount of distance there that it takes for you to gain 40 feet of altitude. Right, and that's, if I had to guess, probably several hundred feet horizontally that gains 40 feet of altitude. So, said differently, as you're hiking along this trail, at least along in this part, there's a lot of separation between the contour lines, and that means it's not that steep. It's not nothing, but it's not that steep. Okay. All right. By contrast, suppose that instead you decided to be a hero and just climb straight up the side of the mountain like that. That is bonkers steep. Because notice, again, you're crossing contour lines, but instead of having several hundred feet to make it across, one contour line, gain 40 feet of altitude, here you have just a few feet, right? And over that much shorter distance, you gain the same 40 feet of altitude. Everybody see what I'm talking about there? So, I mean, I think that is a pretty useful point of view. It tells you, just from looking at this picture, and again, two-dimensional picture, right? There's nothing. This is two-dimensional picture. From the two-dimensional picture alone, I can tell that it's steep in this direction and not so much in that direction. This is very useful when you're hiking. By the way, you'll notice that that is not where the trail is. I hope you might be able to notice anyway. Here, I'll zoom in so we can see a little bit better if I can. There we go. Notice they don't have you going straight across like that. They do this zigzaggy thing. These are called switchbacks. And why do they do this? Well, because if you didn't have the switchbacks, you would have to go, for example, from here to there, which gains you 1, 2, 3 plus a little, probably most of 150 feet of altitude gain over a pretty short distance. That's super steep. And, I don't want to do it, right? So much easier is to walk kind of over this way, kind of not exactly uphill, kind of just barely a little bit uphill, and then come over this way like that. And I gain the same total 150 feet of altitude, but over a greater horizontal distance, and thus it's not as steep. And it's just a little easier going for those of us who need that. Does that make sense to everybody? Okay, so much more pleasant hike going that way. And then the last thing I'm going to point out is if you get onto the peak itself, notice how ridiculously close together the lines are along in here. I mean, that's bonkers close together. It's super steep. It's so steep that when you're standing there and looking this way, it's like 1,200 feet straight down. It feels straight down. Right now, it's clearly not exactly straight down, right? But the slope here is extreme. It's actually about like this. It feels perfectly vertical, right? Because it's scary, right? But it's actually probably about like this. It's probably like 80 degrees, something in that range. And again, you don't have to actually get there to see that is in fact that steep. You can tell that it's that steep just because of how close together the contour lines are. Lots of useful information that you get from, in fact, looking at a bunch of level sets. Is that cool? All right. Now, what we're looking at here are the level sets of a function that has two input variables, longitude and latitude, and one output variable, altitude. We can draw graphs of such functions, right? So why didn't I just use a graph instead of a bunch of contour lines like this? And the answer is the graph would be a three-dimensional thing, right? And I guess I could make a paper mache model, right? That graph would be basically a little miniature model of a mountain, but no one's going to carry around this big, bulky, three-dimensional thing, right? It's just not practical. Much more practical to have something like this, which you can have on a piece of paper and fold it up and put in your pocket, or more realistically these days, I guess you get the app that has it on your phone, but your phone has a two-dimensional screen, right? So much more practical in this case. Okay. All right, so moving along. Graphs and level sets are different, right? The construction that we use to create graphs is very different from the construction we use to create level sets. That said, there is a cool geometric relationship between them. This is very nice, and you can notice it pretty easily. Here's how you make a graph. A graph of a function f is what you get when you set the function equal to a new variable. In this case, I'm calling it z. And if I were to take that graph and then do a horizontal cross-section of that graph. Now let's think about what would it mean to take a horizontal slice? Right, a horizontal slice like this, well, that means we're looking at this plane, and this plane is, well, being it's horizontal, that means z is equal to a constant. So, in fact, a horizontal cross-section is what you get when you just impose that z needs to equal to some constant. And, well, in fact, check it out, what you get as a result of taking a horizontal cross-section of the graph is you get effectively a level set. F set equal to a constant, F set equal to a constant. So, level sets are horizontal cross sections of graphs. It's a nice punchline, and I'm going to show you an example of this in action. So here we go. Some of this I'm going to have to ask you to take on faith, but we'll fill in some blanks later. If you let's suppose we're interested in this function right here. So this is a function with two inputs, one output, x squared plus y squared. Level set, don't forget, means you set it equal to a constant. The level sets are easy to write down. Right, they're concentric circles. We talked that through previously. No problem. Okay, but now let's talk about the graph. The graph is what you get when you set the function equal to a new variable. Here I'm going to set x squared plus y squared equal to z. Here's where I'm going to have to ask you to trust me. We will fill in this blank on Wednesday, right? It's going to be very, very soon. What that looks like is a kind of a bowl. Again, for the moment, just trust me on that, but we will get to why I know that's true. And now let's take the horizontal cross section by, again, setting z equal to c, and of course z equal to c, a horizontal slice by a horizontal plane, like so. And putting these together, x squared plus y squared equals c is what results. And those are indeed circles, just like the level sets. And one little annoying little asterisk. Okay, technically, these circles live inside of a three-dimensional space, and these live in a two-dimensional space. Yeah, fine. Okay, well, what I meant when I say that these are the same as these is if you look at the x coordinates of these circles, they are identical to the x and y coordinates of these are the same as the x and y coordinates of those. Okay. All right. Okay, let's see here. Okay, so We're not going to be able to get through the rest of this page today, but I just want to plant a quick thought before we go on, and that is, again, I've made this warning that you got to be really careful about these different kinds of pictures that we draw, these different kinds of constructions that we use to understand multivariable functions. And in this case, I want you to notice, and we'll go through the details next time, but there's one line in discussion here. And note 3 different functions, very different functions, that we use to describe this line in different ways. And I claim, again, details to come later, this line is the graph of that function. It's a level set of this function. It's parameterized by this function. All 3 of these functions are importantly different. So if you're going to do calculus, calculus is something you do to a function. Which function? And you got to get it right. If you apply the right calculus ideas to the wrong function, look how different these functions are. If you use the wrong function, you're going to get dramatically wrong answers. More on this next time. See y'all later. Have a good day.